Hi everyone, and welcome to Eric's Electronics Workbench. In this video, I'll be showing you how to make an adjustment to the time-based oscillator in this Hewlett-Packard 5334B frequency counter using an oscilloscope and an extremely accurate external 10 MHz reference oscillator. Now this procedure that I'll cover can be used on other devices as well when you need to accurately set an oscillator's frequency as reference to another oscillator. Now in this frequency counter there's another repair that needs to be done, and it became obvious when I took the top cover off. So we'll get into that as well. So let's get started. Okay, here we are looking down on the top of the Hewlett-Packard 5334B frequency counter. So before we get into any repairs or adjustments, let's take a look at the general layout inside the frequency counter. So starting in this corner, we have the AC power coming in. There's a fuse holder and some components that do some filtering on the AC line. We have the primary of the main power transformer and then the secondary of the transformer. Hidden from view from the camera, but down in here there's a bridge rectifier that's converting the AC voltage from the secondary into DC voltage. The main filter caps. And then back on this back panel, which acts like a heatsink, there's a row of power transistors or possibly voltage regulator integrated circuits that act as voltage regulation for the rest of the circuitry in the frequency counter. So this forms the basic power supply in the frequency counter. Now when this frequency counter is turned off, meaning the front power switch over here is turned off, there's a little LED that remains turned on, which indicates it's in the standby mode. And the reason it has a standby mode is because this ovenized crystal oscillator needs to remain turned on at all times. So some of the circuitry does remain energized even when the power switch is turned off. So always remember that some of this is active all the time. Now over here we have a time-based oscillator that all 5334Bs have installed, so the circuitry right here. This is also a time-based oscillator, but this is the high stability ovenized crystal oscillator, which is an option. So this is not always installed. It can be added later. It just plugs in. It's very easy to install. If you don't have this option installed and you want to add it later, there's a jumper wire over here that has to be cut, which disables the original standard oscillator. The adjustment for this oscillator is right here, which you access through the back panel. This adjustment has no control or effect on the ovenized crystal oscillator. So the adjustment on this oscillator is through a little hole right here. So we'll be adjusting this oscillator a little bit later. Again, this one is out of the circuit and we won't even worry about it. That adjustment is not needed. This is the back side of the HPIB connector, which allows for remote control of the instrument. HPIB is basically Hewlett-Packard's interpretation of the GPIB bus. So this is, again, an optional control. It's not needed because all of the instrument's control can be done on the front panel buttons and switches and so on. The GPIB or HPIB interface circuitry is right in here. So the main signal processing and control is in this front half of the circuit board. Starting over here, we have the input side from the 3 different input channels on the frequency counter. There's some filtering, attenuation, and so on that happens over here. There's analog to digital conversion, and over here is the digital portion of the frequency counter. There's also an interface between the main processor and the external HPIB bus, if that's being used. Okay. There's display drivers in the circuitry which drive the LED display, as well as the various indicator lamps that are inside the buttons. Many of the buttons on the front panel have an LED built into them to indicate, active functions and so on. So all of that control takes place in these components over here. So as I mentioned, this has the ovenized crystal oscillator installed. So one of the things we'll be doing a little bit later in the video is to make an adjustment to bring this to precisely 10 megahertz. Now for those of you that aren't familiar with what an ovenized crystal oscillator is, I'll explain. So when you see a device like this right here, this is a crystal which makes up part of an oscillator circuit. This crystal is just, it's by itself, it's in a little metal can, the 2 leads that come out of it. But this crystal is of course exposed to the ambient air temperature that's inside the instrument, so as the instrument warms up, air temperature changes. This can vary a little bit, the circuitry around it can shift a little bit in frequency. Some circuits can tolerate that. It may not be a circuit that's having an effect on the accuracy of the instrument. So that's perfectly fine. You'll often see crystal oscillators that are just like this. However, the time base oscillator in a frequency counter needs to be very, very accurate, and the less drift it has and the more stable that it is, the more stable and the more accurate the frequency will be on the readout on the frequency counter. So when this oscillator drifts a little bit, there's an error or a drift in the displayed frequency. So the idea of an oven is because inside of here there's an insulated box. This is a metal box on the outside. There's an insulated layer and then another box on the inside that houses the electronics and the crystal. So the idea of the oven is because it's kept warm all the time, and it's not a heating element, so to speak. It's really a power transistor that has a current flow through it all the time, and as you may be aware, when a power transistor has current flowing through it, the transistor gets warm. So they're just using that dissipation of the heat to keep things warm inside of here. And the internal temperature inside of here is well above ambient room temperature. It's considerably, pretty hot inside, and it's kept warm all the time. There's also basically regulation circuitry to protect from over temperature and to control that temperature. So the temperature itself is held very constant, and that in turn keeps the electronics in here immune from external temperature variations, which then cause drift and instability. So when you see the term or hear the term ovenized crystal oscillator, you immediately know that's going to be a higher stability, more accurate time base. Now in my previous video, I had mentioned capacitors that were failing that are known as Rifa capacitors, R-I-F-A. So if you haven't seen that video, you may want to check that out now. Now in this frequency counter back here on the AC line input right here, and this filtering, we see 1, 2, 3, and 4 Rifa capacitors. So as I mentioned in that other video, when you see Rifa capacitors that are in an older instrument, and this certainly would qualify as such, they need to go. These things are just a little ticking time bomb, waiting to fail. And what makes things worse in here is these are on all the time. These are across the AC line, which is not switched. So the main power switch is over in this corner. You can see the traces on the board right here that are part of that, actually, that go to the switch right here. And they're really switching the secondary on the transformer. This is not switched. So if one of these goes, it is right on the AC line, and it's not even going to be switched. You certainly would hope that the fuse fails or something protects things, but if one of those goes, it is right on the AC line. Now these are known as safety capacitors, and they're supposed to fail in a safe way, but the manufacturer didn't intend for them to start having failures that they're having now, which is that the cases on them, the plastic case, is starting to crack. Now in my previous video, the capacitors, they didn't look too bad. They're aging and they needed to be changed out, really just as a precaution. Well, I'll zoom the camera in here and I'll reposition things in a little bit. These look terrible. They haven't failed. This does power up. I have turned on this frequency counter. It is in working condition. It's just a little bit off because of the setting on this crystal oscillator time base. So these still work. They haven't failed, but they have cracks all in the case. So they're a very good example of what they look like when these Rifa capacitors, have aged and really are ready to fail at any moment. So let me position the camera and zoom in a little bit closer. You can see what's going on. Here's a closer look at the 4 Rifa safety capacitors that are starting to fail in this frequency counter. So you can see this one right here, here, small capacitor here, and then this one right here. So these large capacitors are X2 rated, the small capacitors are Y2 rated safety capacitors. And you can see the failure is the cracking in the case. So if I shine a light in here, you can kind of see all that hairline cracking that's forming. It's a little bit harder to see sometimes on this different angle, on this one on here. This one back here is very visible. So again, all that cracking that's on the side of the case, like a hairline crack in there, you can really almost feel it if you run your fingernail along the side of the capacitor. You can almost catch your fingernail in those cracks. So pretty substantial. And when they start to fail with that cracking, it begins to allow moisture to get into the capacitor. When that moisture works its way in the capacitor, they just completely fail. and they basically do so in a pretty spectacular way. Now, these are safety capacitors, and the manufacturer intended them, if they were to fail, it would be because of a voltage surge or something like that, and they would fail in a safe way. They would go to an open circuit, or in X2 rated capacitors, they're self-extinguishing. But the manufacturer didn't anticipate for them to start failing with cracks in the case and you know, that type of a failure mode. So when you see these older capacitors, they really need to go whether they have cracks or not, because they'll definitely crack over time, even if they appear to be okay at the time that you see them. When they're 30 some years old, they definitely need to go, because they're basically at the end of their useful life. Now, the ones that were in my previous video that I was showing, they had some minor cracking, not nearly as much as these have, so it does vary. But these are pretty bad. They definitely have a lot of cracks on the side. So they are going to go, and we'll get them replaced. Now, to replace them, I need to have access to the bottom of the circuit board. And to do that access, or get access to the bottom of the circuit board, really involves dismantling the entire frequency counter because of how it's constructed. If I zoom the camera back out a little bit here. On the sides right here, this is riveted together so the back panel doesn't come off. The sides are wrapped around. This aluminum is all this, it's perforated on the side for a vent. It goes down around the side, but it's all formed. It's the same piece. So the bottom of the chassis and the sides are all the same. So what you have to do is take the front panel off up here, and then remove this circuit board basically after the front panel is taken off. But I also need to take this transformer out and the heat sink that's up here associated with that, because the circuit board goes underneath this heat sink right here, so it's basically trapped around this transformer. So a fair amount of disassembly, but it'll all come apart, and got to do it because those capacitors need to go. And again, these are not switched. They're hot all the time when this thing is plugged in, so we definitely don't want those failing at any time. So I will get started on replacing those capacitors, and I'll be back when I have the frequency counter taken apart. The frequency counter is disassembled, and I have access to the bottom of this circuit board, so I'll be able to desolder the components on here that need to be replaced. Now, as you see it disassembled, it gives access to some areas for cleaning that you don't normally have access to. For example, underneath this circuit board where it sits in the main chassis, it's mounted on those standoffs, and there was some dust and lint, so that's been cleaned up with compressed air and a bristle brush. Now you can see the front panel is sitting back there. It's facing downward, so we're looking at the back side of the front panel. I used an anti-static bristle brush and some compressed air, cleaned that circuit board and the areas around it. I also cleaned this circuit board with the anti-static bristle brush and some mild compressed air, so it had just some dust that was on it, but it cleaned up, so it's looking very good at this time. So the components that I'll be replacing, as I mentioned, the safety capacitors, and there's 4 of them. So right here we have the new safety capacitors. So these are 0.1 microfarad, all right, X2 rated, and you can see on these they say 100 N, so that's 100 nanofarad. If I get the light on there, I think you can see it. But anyways, 100 nanofarad is the same as 0.1 microfarad. And these, the writing's pretty small on them. These are 2200 picofarad. I don't think you're going to be able to see that too well on the camera. A little bit of a glare anyways. But anyways, 2200 picofarad, Y2 rated capacitors. They're actually X1 Y2 rated, so they have both ratings on these. So we'll get those replaced. Now I'm also going to replace the electrolytic capacitors that are part of the power supply circuit. You can see them with the blue can right there. So those 4. Now all 4 of those capacitors are rated the same. Each one is 4700 microfarad at 35 volts. So here are the replacements that I'll be using for those. Gather those right here. So I have right here. And these are Nichicon, very high quality capacitors. So they're a direct replacement. Anytime you replace a capacitor like this, you always want to check your lead spacing, make sure that they mount correctly. These have the standard 10mm lead spacing, so they just will drop directly into the circuit board, very easy to change out. So again, Digi-Key, very high quality capacitor. So they'll be good for the long term. Now the reason I'm replacing these electrolytics, there's no indication that the ones on that circuit board have a problem currently, but we want this to be good for the long term, and it's an instrument that's going to be used on the workbench here. It'll see use very often, and the last thing we want to have happen is one of those capacitors to fail after we've done all this work to take it apart. And we're right here, very easy to change them, so now's the time to do that. And this instrument is pushing 30 some years old, so those capacitors have quite a few hours of use on them. So again, now is the time to change them out. Now I'm often asked where I source the components that I use in these projects, the components that I purchase to do the replacements. And when I'm doing this type of work, I personally don't like to use used components. I would not take these capacitors and find used takeouts from another instrument and put in here. I always use new. I think it's a much better way to go. Reusing used components, particularly electrolytics, can lead to problems. Resistors and some other components you can reuse, but cautiously I would test them and make sure that they are in good shape. You don't want to be putting old components in that have drifted in tolerance or something like that. So just common sense. But when I need to purchase new components, my go-tos are Mouser Electronics and Digi-Key Electronics. In this case, the capacitors that I just showed you all came from Digi-Key. Both Digi-Key and Mouser have a very large selection, and they're really my two go-tos for the projects that I work on. They're in no way a sponsor. They're just two companies that I have dealt with for many years, and certainly recommend. Now, something you should be aware of on components just in general, whether it's transistors, capacitors, so on, integrated circuits, etc., are fake components, aftermarket or fake components, and the market is really flooded with them. So when you're purchasing components, you always want to go to a distributor that has a system in place that they're checking for fake components, and that they're only purchasing and guaranteeing that they're purchasing from reputable sources direct from the manufacturer. So for example, these Digi-Key capacitors, Digi-Key is an authorized distributor, and these are genuine original capacitors. They're in no way a fake or a look-alike. So you want to be very, very careful with that. Transistors in particular can be a very big problem. Fake transistors that claim to be the real thing. They have the right part number, but are in no way, shape, or form close. If you dissect it and look inside, you'll often find that they're just an absolute look-alike. So be cautious of that, and just be aware of what's on the market out there and who you're purchasing from. So I'll get things positioned a little bit different here, and we'll get the desoldering tool in place, and I'll pull the components off the board. Okay, I'm ready to desolder the old components and remove them from the circuit board. Now the procedure is the same for any of the components that I'll be removing, so I'll just demonstrate on two of the capacitors. I'll start with the two larger 0.1 microfarad safety capacitors. So I'll just be using my desoldering tool. You can see here it's just a vacuum desoldering tool. So you just come in here like so. The tool on the pad, heat. Remove the solder. You could hear the component fall off when it heated the second pad, and then you just vacuum out the solder that's on the pad, but the component just falls off on the other side. So very easy to remove. Let's see, the other capacitor is across here. Like so. Again, that did the same thing. It just falls off when you heat that second trace, or second pad on the trace there. And we have the two capacitors removed, so just that simple. Now we can take a look. I had previously mentioned the cracking that had formed in those capacitors, so if I go like this, and let's see here, get this in the camera, move the circuit board out of the way there. So you have this zoomed in here, so we've got the old and the new. On this side you can see here. You can kind of see it. Unfortunately there's a lot of glare, but you can see how the new capacitors look very smooth, you know, no flaws or defects in the plastic. And these old ones, you can see there's just a lot of hairline cracks that run, you know, through that plastic. If I turn them there, you can kind of see. So that's what you want to look for when you're inspecting these. Really, if you think they're, you know, have, you know, 30 some years of age on them, they need to be changed no matter what. But when they do get the cracks in it, it's pretty obvious. They tend to get it on both sides. The plastic just gets a very dry look to it, just cracks and becomes very brittle. I guess it just falls apart. When they start to overheat, you know, a lot of times they'll split, but by the time they do that, they often just completely short and completely fail, turn into a little briquette, a little chunk of charcoal. So there you have the capacitor removal, and I'll show how to solder the new components in when I get the rest of these removed. So I'll do that and I will be back. I'm ready to install the new safety capacitors on the circuit board. The 4 old ones have been removed. So the procedure to install the new capacitors is the same for each one. I'll just demonstrate on the first one. So when you're installing these capacitors, the orientation that they're on the board does not matter. So it can install this way or this way. It does not matter. There's no polarity to the capacitor. So take the circuit board and bring it down here so you can see. One of these 0.1 microfarad capacitors went right here. All right, so it just goes right into the board like so. And then while we hold the capacitor so that it's tight up against the board from the bottom side, you want it all the way up, not standing out away from the circuit board. Just give the leads a little bit of a bend to the side, like so. All right. So again, if I turn the board here, you can see bring this down here. The capacitor is against the board, all right? You can see how it's sitting there. Pardon the beep, that's just the soldering station telling me that it is up to temperature. So we'll just come in here and make our solder connection, make sure it's on the camera. Yep, you can see that. All right, like so. And then just trim the excess lead length right off, like that. And that capacitor is installed. Bring that down there, you can see it. So again, the procedure will be the same on the others. So in the previous part of the video, the view from the camera while I was soldering was partially blocked by my hand and the soldering iron. So it may not have been obvious how I was soldering or what the procedure was. So I'll demonstrate again on this connection right here. So if you're new to soldering or learning how to solder, I'll share some tips that will be beneficial to you as well. So when you're soldering, you always want to heat both the circuit board pad and the component lead, okay? So you're going to come in here and you're going to touch both at the same time, and then you're going to feed the solder in while keeping that pressure and touching both the component lead and the pad. You're going to feed in enough solder so that you do get a small puddle, but it's not excessive. Of course, you don't want the solder, you know, spilling over. If the traces are very close, you can end up getting a solder blob or a solder bridge between pads, and of course that would lead to a disaster and a short circuit. So only enough solder to make the connection. If it's a plated through hole, enough solder that the solder is able to flow through and wick down through the plated through hole. So plated through holes take a little bit more solder than if it's a non-plated through hole. But again, you're just using enough to make the connection, nothing too excessive. Now I use 60-40 solder, all right? And it's electrical grade solder. Never use plumbing type solder or solder for other applications, it always needs to be electrical grade solder. All right. This solder is 0.031 inch diameter, so that's a very good size for general use on circuit boards like this. I find it to work very well. There are other diameters of solder, but again, this is 0.031. This is a rosin core solder, and it generally does not require a flux to be added to the circuit board, but if you're having trouble getting the solder to flow or the solder to take, while you're soldering, having some issues, you can add a flux to the circuit board. Again, it needs to be an electrical grade flux. Never use a flux that's intended for soldering like on a plumbing or copper pipe. You need to make sure that the soldering iron itself is hot enough. So if the soldering iron has an adjustable temperature range, it should be appropriate for what you're working on. Obviously, smaller connections, more delicate components, you can turn the temperature down. And if it's a larger pad, something like right in here where it's a much larger area that would conduct the heat away, if you're soldering on that, you need to have more temperature, a hotter tip on the soldering iron. Experience and just using the soldering iron and adjusting the temperature, you'll find what works well. If the temperature is too cold, the solder just won't take. You'll feel like when you're soldering, it's just not flowing. It just seems to almost, ball up and just stay. It doesn't flow correctly. So it's, obvious when when the temperature is not enough and it's too cold. But again, that's just experience. You don't want a temperature that's too hot because you can damage the trace, so you don't want to overdo things. And you also don't want to spend a lot of dwell time in here soldering and really keeping the temperature, because again, you can damage the components, you can damage the trace on the circuit board. So again, experience, you'll get a feel for what the amount of time is and how long it takes to make the connection and what the right temperatures are. Now for this, I have this set for 750 degrees. I generally work between 700 and 750 degrees Fahrenheit. I find 750 degrees is a good temperature. It's hot, it gets the solder to flow quickly, you're not spending a lot of dwell time, and that's pretty much a go-to temperature that I use on a lot of components. Traces like this also tend, this is a little bit larger trace in here, this tends to pull away the heat from that connection, so you do need to have enough temperature that you're not spending a lot of time trying to heat that point, because that can damage components. And again, you're keeping things very clean. The tip on the soldering iron is tinned. You keep it clean. There's no corrosion or oxidation or anything like that on the soldering iron tip. And the soldering iron tips do get dirty while you're using them, so it's important to continuously clean them. And I use just the coiled brass type cleaner. You can also use a damp sponge. The coiled brass cleaner works very well, and it doesn't have a thermal shock while you're soldering. So we come here like so. Heat the connection. You can see how the solder flows very well around there like that. And you can tell a trace like this, it does pull the heat away from that connection while you're soldering, compared to, and I'll go over here, this trace right here, where it's on the end of the trace, typically will solder considerably faster. You can see that one took quite a bit faster because the pad is right on the end of that trace, where this is in the middle, takes a little bit longer. The last four capacitors that need to be installed are the 4700 microfarad electrolytic capacitors. Now, electrolytic capacitors, for the most part, are polarized, meaning they have a polarity, a positive and a negative lead on them. There are some types of electrolytic capacitors that are non-polarized, but again, for the most part, the ones you'll come across are polarized, and it matters which direction that they're installed on the circuit board. If they're installed in the wrong direction on the board, they'll quickly fail and oftentimes explode. So you can see on the capacitor, it's polarized when the lead is clearly marked. We have a negative lead there. It's also cut shorter, which is a visual reference. The shorter lead is the negative lead. Sometimes the positive lead will be marked. You can see on this one, they are not marked, just the negative. So we know it is a polarized capacitor, and it needs to go in the correct direction on the board. Now, I noticed before I removed the original capacitors, all 4 capacitors had the negative terminal or the negative lead on this side. So I just put a little dot on the circuit board right here as a visual reference that all the capacitors need to have the negative lead facing this direction. Now, it's not uncommon to find circuit boards where the capacitors have a negative lead going this way and the next one will be going this way and so forth. So it's very important to note the direction. Some circuit boards will have a positive or a negative mark next to the pads on the circuit board. This board does not. Now this circuit board does have a square and a round pad. The square pad is actually the positive, but if you're not familiar with that, that marking and what they mean by the square versus the round pad, it wouldn't be very obvious necessarily what the polarity should be. But it makes it very easy if you just take note on the original capacitors and which direction they were installed. So again, I made a note of that before I pulled them off the board, and the negatives are all facing this direction. So when this capacitor is installed, of course it will go like this, the negative lead going this direction, and the other 3 will be the same. All right. So I'll get those installed, and I'll be back when the frequency counter is reassembled and we're ready to make some adjustments on the Ovenized crystal oscillator. The Hewlett-Packard 5334B frequency counter is now reassembled, so we're ready to power it up and see, will it work with these new components that have been installed. If it powers up okay, it does have a self-test. If that passes, then we'll proceed with some internal tests and adjustments. Now, if you're following along and working on one of these units, please know you do so at your own risk. Of course, when you're making the internal tests and adjustments, the top cover needs to be removed for access, to the internal components. And of course, that does expose some AC line voltage in that back corner back there. So take care. Know the risks and dangers when working on a piece of equipment like this, particularly with the exposed AC line, because again, you do so at your own risk. Previously in this video, I had mentioned that if you have one of these frequency counters that relies simply on the standard oscillator, which is back there on the circuit board, and you wanted to add the Ovenized crystal oscillator, which is right there, when you add that oscillator, I mentioned you cut a jumper wire to disable the standard oscillator. Well, that's incorrect. I was reviewing the schematic and realized that that's in error. There is a modification that has to be done, but it's not just a jumper wire. It involves a capacitor and the crystal in the original circuit. So let me grab the schematic. I'll reposition the camera a little bit, and I'll just briefly show what's involved on changing that over. This could be beneficial to anyone that has one of these frequency counters and wants to add the Ovenized crystal oscillator, because it really is a simple upgrade and enhances the accuracy of the frequency counter considerably. Now, that Ovenized crystal oscillator, the Hewlett-Packard part number is 10811-60111. They're readily available on the used market. Here's a portion of the schematic for the frequency counter, and we can see right here the standard oscillator circuit, and right here is the edge connector for the Ovenized crystal oscillator. So this connector is on the main circuit board, and the Ovenized oscillator just plugs into it. Right here where it says OSC, that's the output signal from the Ovenized crystal oscillator, all right? And this is the original standard oscillator, and its output signal comes right here. So we have, it says C note 6, and we have 2 capacitors, C8 and C100. Note 6 is just mentioning that you don't have both of these capacitors installed at the same time, all right? Because this oscillator or this oscillator, you're only using one, of course, and ultimately the signal is coming up here through a switch, internal-external selection switch, and then off to some additional circuitry. So if you do not have the Ovenized crystal oscillator and you want to add it, what you'll find is that you have crystal Y1 installed and C8 will be installed. So this oscillator, of course, is active. And what we need to do is disable this oscillator. So the procedure for that is to remove Y1. So you just simply desolder from the circuit board, remove Y1. That disables this oscillator. And C8 is simply moved over to the C100 position, leaving this as an open connection right here. You can see C8 and C100 are the same value. So you can just simply move C8 over to C100, and then when this Ovenized crystal oscillator is installed, the signal is able to pass through here. This is open right here, so the signal comes up, and again comes through the switch and ultimately goes to the additional circuitry. So very simple modification, but I wanted to clarify because you're not cutting any jumper wires, you're actually removing Y1 and moving that capacitor. This is also a good time to point out the safety capacitors that I just replaced because they're right here on the schematic. All right, so I'll explain what's going on with this circuit and why these need to be safety rated capacitors. So we can see right here we have the AC line coming into the instrument. The top right here is the hot AC line. The middle is earth or chassis ground, which is denoted by that symbol. That's the connection to the chassis ground. And then the bottom right here is neutral. So right here the hot AC line comes into F1, which is the fuse. And then we have these inductors right here, and then the 4 safety capacitors. So this circuit is providing filtering on the AC line, noise removal, RF removal, things like that on the AC line, so that the AC coming into the instrument is clean and does not have any noise or anything like that on it. Now you can see that C210 and C207 are 0.1 microfarad capacitors. And you can see that they're connected directly across the AC line. So anytime you have capacitors that are across the AC line, so we have the hot up here and neutral down here, so directly across the line, those need to be the X class capacitors, very often X2 rated capacitors. Now, right here we have C209 and C208, the 2200 picofarad capacitors. And you can see there's that triangle symbol again, all right? So when you see that triangle symbol here and here and here, those are the chassis ground connections, all right? So those are all considered the same point, that's the chassis, a common ground connection in the instrument. Now you can see that these capacitors, one of them is from the hot AC line to the chassis, and this is from neutral to the chassis. Again, when you have a capacitor that's connected on the AC line, whether it's the hot side or the neutral side, it needs to be a safety rated capacitor, and these must be the Y class capacitors, very often Y1 or Y2 class capacitors. The reason that these need to be safety rated is so that they fail in a safe way, because if these were to fail, they're designed to become an open circuit so that you do not connect the AC line directly to the chassis. Now when these become an open circuit, they of course lose their capacitance ability or what they're doing in the circuit, but that's a lot better than having the AC line connect directly to the chassis, which could cause shock hazards and all kinds of other problems. So again, these fail in a safe way. These capacitors here that are the X class capacitors are self-extinguishing. So again, if they were to fail and short, they're self-extinguishing, so if they catch on fire, again, they will go out, and they're designed so that, you know, an external fuse will blow, but again, they fail in a safe way and contain the failure to that capacitor. So when you see capacitors, again, across the AC line or line to a chassis ground connection, they must be safety rated. If I move the schematic over just a little bit here, keep this on the camera, I can show you the electrolytics that I replaced, those 4 electrolytics. You can see right here, there's a 4700 microfarad electrolytic right there, right here, and then these 2 right here, which are in parallel. So these are being used together. So basic filtering, this is a linear type power supply, not a switching power supply. You can see over here we have the voltage regulators, integrated circuit voltage regulators that are on that back panel. So a very straightforward type power supply. And over here there is only one adjustment for the voltage in the entire instrument. These are fixed voltage regulators and there is no adjustment, but there are test points. So because we've changed these filter capacitors in here, we want to make sure that all of these voltages are looking okay, that there's no issues going on, so we'll take that measurement once we power up the instrument. But this adjustment right here is the only adjustment for a voltage, and it affects the 3-volt supply. So we'll take a measurement on the 3-volt supply. If it needs any adjustment, it's R202 is the adjustment for that. So let me reposition things, and we'll show you where I'm going to take some voltage measurements, and also we will power up the instrument and see that it turns on okay, and if everything looks good, then we'll take some voltage readings and then move on from there. So let me get things repositioned. All right, moment of truth. Let's power up the frequency counter and see if it functions correctly with the new capacitors that have been installed. Now I have the frequency counter plugged into an isolation transformer and a very light fuse protecting the isolation transformer and of course this instrument. So if there is a problem, that fuse will just go away and it'll protect things and keeps things very safe that way. And the isolation transformer is good practice when you're working on an instrument with the cover removed and you're working around that AC line. So again, good practice to use an isolation transformer. However, never ever use a dim bulb tester or a variac to slowly bring up the voltage on solid state devices. So you'll often hear about dim bulb testers and using a variac along with an isolation transformer for vacuum tube equipment. Perfectly fine to do so. I've demonstrated that on this channel. It's a very safe way to test vacuum tube equipment, but again, never ever use a dim bulb tester and a variac to slowly bring the AC line up on solid state devices. To do so can damage the device, and it'll certainly put the device into an indeterminate or in between sort of state. It won't be happy. The voltages won't be correct. They're not made to work that way. It would basically be like putting a very low AC line voltage into the instrument, and it can cause problems and damage. So again, don't test with a dim bulb tester or low AC line voltages on solid state devices. All right, I'll turn on the isolation transformer. All right, that looks good. You can see down here we have the standby indicator lamp. So the power switch is off right now, and the standby is just indicating that there is power being applied to the Ovenized crystal oscillator. Okay, here we go. Let's try it. Lamp test, and it does pass. Self-test passed, and it looks very good. So that is a normal indication now. It's just all dashed out on the display right here because there is no input signal. These lamps flash over here. Everything looks very good. All right. So the next thing that I want to do is check the DC voltages on the board. So let me zoom the camera in and I'll show you the test points that I'll be testing. Zoom in a little bit more here, and I think you can see this. Tip this up a little bit here. So right in here, see there's a group of pins that stick up on the circuit board, all right? And those are the test points for the DC voltages. Now again, there's only one adjustment for the power supply in the whole instrument. The other voltages are fixed, so either they work or they don't. If they're out of spec, there's a component that would be faulty. The 3 volt has an adjustment, and the specification in the service manual calls for 3.00 volts plus minus 0.02 volts. So we'll look for that accuracy and see if that 3 volt supply is within specification. If it's not, we can make an adjustment on that. So what I'm going to do is take the measurements on these points down in here, but I'll put the camera on the voltmeter display. So I'll call out which pin I'm probing on, and you'll be able to see the voltage reading that we're getting on the circuit board. I think that will work better than trying to go between this board and then up to the display on the digital voltmeter. It's just a lot of moving of the camera. So let me position the camera over to the voltmeter, and then I'll start taking the measurements. All right, here we are looking at the Hewlett-Packard 3456A digital voltmeter. So you can see it's set to DC volts and it's auto ranging. Now the numbers that you see fluctuating around on the screen are perfectly normal because the ground test probe is connected to a ground point on the circuit board in the frequency counter. It's a test point that they call out to use when you're measuring the voltages for the power supply. And the positive probe is just floating right now. I'm touching the end of it. You can see it causes it to change a little bit more right there. It kind of fluctuates around. And then when I just lay it down there, it kind of goes back again. So it's just picking up some noise and things like that. So perfectly normal to have those numbers fluctuate. Now if I short the probes together like this, you can see that falls to a very low value, all right? So again, when they're disconnected, they float and the voltages fluctuate around a little bit. So perfectly normal. That's just something that happens. So I'll call out the voltages on each test point as I move through them, and we'll see if the readings we get are within specification. So the first test point is a positive 5 volts, all right, and it's on the analog circuitry. and that looks very good. We see 4.966. Last digit fluctuates a little, not a problem. Very stable, so no problems there. The next test point is the positive 5 on the digital circuitry, and that looks very good. We have 5.005, slight fluctuation on the last digit, no issues there. The next test point is a positive 12 volts, all right, and that looks very stable. Looks very good, no problems, 12.011. The next test point is a negative 5 volts. So negative 5.089, and then a little bit of fluctuation on the final digit, so no problems on that one. Looks very good. And then the last test point is positive 3 volts, and that looks very good. Now that's the only voltage that could be adjusted, but it looks well within spec, no problems at all. 3.00 and then 5, little fluctuation, 6 or 7 there. No problems. The specification in the service manual calls for 3.00 plus minus 0.02, so well within spec. 0.02 would be 20 millivolts, so not a problem there. So all the voltages are looking very good, no issues at all. So the next thing that I need to do is position things to take a measurement on the internal ovenized crystal oscillator, but the instrument needs to run for 24 hours before I do that. So I'll let it sit here, and then I'll get things connected, and then we'll take the measurement and set that internal oscillator, because I do know that it's off just a little bit, so we want to bring that into specification. We want to bring it right to 10 megahertz. Now, the reason it needs to run for 24 hours is because this oscillator, the ovenized crystal oscillator, is on all the time, and it needs to stabilize and come up to temperature before you make any adjustments. If you make an adjustment on it and it's not up to a stable temperature, then you might come back, a day or two later and find that your adjustment has drifted a little bit. So once it comes up to its normal temperature internally, it's very, very stable and won't drift at all, but you have to give it time to do so. So again, they do mention 24 hours, in the service manual, so we'll go ahead and follow that and just let it sit here on the bench, and then I'll get things connected, and we'll continue from that point. I now have the Hewlett-Packard 5334B frequency counter connected to my Tektronix TDS380 oscilloscope, and I also have a very high precision reference oscillator connected to the oscilloscope. So I'll explain the overall setup and how we'll be adjusting the ovenized crystal oscillator in the frequency counter. So on the oscilloscope, we have channel 1 input right here, and this signal is coming from the ovenized crystal oscillator in the frequency counter. Okay, so this is a 10 megahertz signal coming in. This is a 50 ohm feed-through termination, so the signal goes through this termination. This applies 50 ohms from the center conductor to the outside shield of the coax. This is very high input impedance on the oscilloscope, so you want to terminate that into 50 ohms because it eliminates any reflections that may occur on this coax. The frequency counter expects to see a 50 ohm impedance. Same over here, this is a very high input impedance, and the external reference oscillator is a 50 ohm output and expects to see a 50 ohm load. So by using 50 ohms over here, feed through termination, it just eliminates any reflections that may occur on the coax. So just good practice to use those. These are not applying any attenuation in the signal. Again, it just goes from one side of that adapter to the other. Now on the oscilloscope, channel 1 again is the counter time base from the frequency counter, and again over here we have the external reference oscillator's input. Okay, this is a very high precision 10 megahertz signal coming in here. So my external reference oscillator is based on a 10 megahertz ovenized crystal oscillator that is synchronized to the GPS time signal. So by synchronizing that oscillator, and it makes minor corrections to keep it precisely at 10 megahertz, it has an accuracy on this signal of 10 megahertz plus minus 100 microhertz. So 10 megahertz plus minus 100 microhertz. Very, very precise signal coming in over here. That accuracy is a higher accuracy than the time base in the frequency counter, and it's a higher accuracy than the frequency counter could display. Always very important when you're making a calibration that your reference signal has more accuracy and is more stable than the signal that you're trying to calibrate. Now when the signal on the oscilloscope rolls, as you see, to the right side, that means that this signal here coming from the frequency counter is lower than this 10 megahertz signal. So this signal here does not change precisely 10 megahertz. This signal will vary as we make the adjustment to the Ovenized crystal oscillator, and right now this signal is just slightly under 10 megahertz because again we see it rolling to the right. Now if this signal rolls to the left, this signal right here from the frequency counter is higher than 10 megahertz. Okay? Now the adjustment in the service manual says that this waveform should not roll or shift more than 1 division in 10 seconds. So that's ultimately the goal, is to have this less than 1 division of movement after 10 seconds. And if it has even less than that, hopefully it's spot on, doesn't roll at all. But again, it can be up to 1 division in 10 seconds. All right, let me reach around to the other side because the camera's kind of between the oscilloscope and the frequency counter. So reach over here and I have a tool that reaches into the Ovenized crystal oscillator. There's just an adjustment in there. It's an anti-static, insulated type adjustment tool. So it reaches in and it's a multi-turn adjustment. And they have an arrow indicating which direction you turn to increase the frequency, which again we need to do because we know that that frequency is just slightly lower. So I will begin to increase it here, like so. You can already see that it is starting to slow down, so that's a good sign there. So I'll increase that a little bit more, like so. So now that's looking very good. Just has ever so slight movement there. Just give it a little bit more. Little nudge, nope, too much. So now you can see the signal is increased a little bit too high. I'll roll in the other direction. Back a little bit here. Very close right in there. So I'm going to stop that adjustment. I'll set the tool aside there. So I'll let that sit for a little bit at that point. What I want to do is make very slight adjustments now that's very, very close. And over the next half hour or so, make little tiny adjustments just to nudge it around, watch it, and ultimately get it dialed in, exactly. I don't want to make an adjustment and then quickly put the top cover on and, then come back later and find that it needed a further adjustment. So we'll take some time and just make slight adjustments, let it sit for a little bit, keep monitoring on the oscilloscope, and I will come back once I have everything dialed in perfectly, and we'll take another look at it. I have the camera zoomed in a little closer to the oscilloscope's display so that we can take a close look at the waveform now that it's been adjusted. I've spent about 20 minutes with just minor adjustments back and forth on the Ovenized crystal oscillator. It's looking very, very good at this point. There's almost no drift. If you study the waveform long enough, you'll see, just a slight shift, but it's very, very slight, very minor, and well within specification. So again, the service manual calls for, in 10 seconds, no more than 1 graticule of change or rolling or shifting on the waveform. So you could pick any of these graticules, but right here where the waveform crosses through, if you look at that, you would not want to see more than 1 graticule of movement in 10 seconds. Well, you can see that I've been talking for longer than 10 seconds and it hasn't changed hardly at all, very, very minimal amount. But we'll time off 10 seconds here and let's take a look at, exactly how much movement there is in exactly 10 seconds. So we'll start now. Stop. All right. So I was watching right where it crosses through, okay, and in that 10 seconds there was virtually no change in that waveform. So extremely precise. So it means that the Ovenized crystal oscillator is working very well and it's really spot on frequency. So the oscillator, the time-based oscillator in the frequency counter is now exactly at 10 megahertz. And that'll be reflected in the accuracy of the frequency counter, the digital display. When it reads a frequency, that frequency can be trusted, it will be accurate now. So it's looking very, very good at this point. Now there are a couple other minor adjustments that I'm going to make off camera. The digital analog converter, channel sensitivity offset, attenuator adjust, some just basic housekeeping kind of adjustments, and a couple things I want to check in the frequency counter. There's not a lot to show. Some of those adjustments involve just applying a signal to the frequency counter and then just taking a voltage reading, something like that. Really straightforward. Again, not a lot to show. So I'll do those off camera. When all of that's complete and done, I will turn the camera back to the front of the frequency counter and we'll take a look at how it's performing. I'll put a couple various signals into the counter and we'll look at the display and we'll wrap things up. So I'll be back in just a little bit. The Hewlett-Packard 5334B frequency counter adjustments are now complete. The instrument is functioning very well. It's been completely reassembled and ready to put back into service. So you can see it's displaying a frequency over here, and we have an input on channel A. So I'll demonstrate a few of the measurements that the frequency counter can make. So right now, the signal that's coming into channel A is from the external reference oscillator, that GPS synchronized oscillator that I previously used. And it's sitting precisely at 10 megahertz. So you can see over here, we do have an indication of 10 megahertz. Now it sometimes will toggle down to all nines, perfectly normal. When it's sitting right at a specific frequency, sometimes it'll do like we see here. Again, perfectly normal that it will toggle between the 9 and then the 10. Now to read the display on here, you can see this is an exponent over here and the indication is given in hertz, all right? So to read this, the exponent of 6 tells us we're going to move the decimal point that way 6 places. I'm going to disconnect that so it doesn't toggle anymore. All right, let's leave that disconnected like so. All right, that'll keep the display constant. It holds the last display if you remove the input. So right now, with a 6 being displayed here, we move this over 6 places. The decimal point moves over. So 1, 2, 3, 4, 5, and 6, okay? So that's giving us an indication with 1 digit past the decimal point, all right? So that would be 100 millihertz, all right? So to read this, you have units, tens, 100,000, 10,000, 100,000, million, and 10 million, all right? So 10 million hertz or 10 megahertz. So the display is very easy to read. You just have to watch the exponent display over here. If it's a negative display, then the decimal point moves that direction, all right? And I'll demonstrate that shortly. So let me reconnect here. Get this back on here. All right. So now it's again reading this signal. So it's reading frequency A, and we can take a look at the period on A, all right? So we can see 100, a decimal point, the remainder is zeros, it toggles between the 9. What I will do is disconnect this. If it goes back again, it might make it easier to follow. It might hold there at 99.99. It's going to stay. Well, we can do the, okay, like that. So we'll just let that hold there. So the period is given in seconds. So this is not, of course, 100 seconds. We have a -9 exponent right here. So it tells us to move that decimal point 9 places to the left, all right? Well, when you do that, you'll find that this is actually a reading of 100 nanoseconds. Well, 100 nanoseconds is the same as 10 megahertz. 100 nanoseconds is also the same thing as 0.1 microseconds. So again, you're moving the decimal point 9 places to the left. All right. Now, this has 3 input channels. So we have channel A here, we have channel B, and then we have channel C input. Channel C input is 50 ohms. These can be high impedance or 50 ohms selectable. I have them set to 50 ohms. This is always 50 ohms. And the channel C input is used for 90 to 1300 megahertz. It will actually read frequencies under 90 megahertz, but typically you use it for just the higher frequency input. So on channel B, we go like so, and we have our indication again. All right, 10 megahertz. Now this has a useful function for ratio measurements. So I'll make this connection back here. So a ratio measurement requires the A and B inputs. And it really is just a ratio between these inputs. Now you can see there's no voltage or hertz or a time indication. Those indicators have gone out over here. A ratio is just simply that. If it says 1, then it's a 1-to-1 ratio between these two inputs, meaning they're both the same. So let me grab the other input here. I have a second function generator set to 10 megahertz, and we'll make that connection here. All right. All right, there we go. So now we see the ratio measurement that this is making between these two inputs is 1 point and then all zeros, which tells us that these are precisely the same as far as the instrument can measure. And it makes sense because this is the very accurate GPS synchronized reference oscillator, and this is a very accurate function generator that I have that is also set to 10 megahertz. All right, so a very useful measurement, way to measure the ratio between two different signals. Now if I come over here to the function generator and drop the frequency down to 5 megahertz, you can now see this is a 5 megahertz input, which is exactly half of this input. So we can see the ratio is 2, all right? Well, this is 2 times this input over here. If I reverse these connections here, now you can see 0.5 or half, okay, because these have just been flipped. So it's just depending on which way you're looking at, which one's the higher and the lower measurement, okay? So now let me demonstrate the frequency on the input C, all right, the third channel. Make a few connections here, pardon the cable movements, jumping around here a little bit. Okay, we'll switch that over. So C, channel C input is not active just yet. I have a Gigatronics RF signal generator, and it is set to 1000 megahertz. All right, so this cable out of the way here. Turn that signal generator on. And there we have it. So that's 1000 megahertz or 1 gigahertz. Looking very, very good. So again, this is a 9 and this is measured in hertz. So this is telling us to move the decimal point over 9 places. So when you do that, 1, 2, 3, 4, 5, 6, 7, 8, 9, we add a 0 right here. That 0 is interpreted to not change at all. It will always remain a 0 for the accuracy. You would just always assume a 0 at that point. So when you count that over, you have units, tens, 100,000, 10,000, 100,000, million, 10 million, 100 million, and 1 billion. 1 billion hertz or 1 gigahertz or 1000 megahertz. All the same thing. So that's looking very good, very accurate, and reading exactly what we would expect to see. So it's functioning very well. So I'll disconnect that connection, and the last connection here to demonstrate will be the count. So if we come over here and the total to start, and we'll come back over here to channel A input. Cable movement. So just a useful function. This is counting 1 pulse per second, all right? So basically every second we're just getting a pulse on this cable coming in here, and it's just simply displaying those pulses as a count. And this can count up to very, very high frequencies. At high frequencies it just becomes a blur, it counts so fast. But again, if you need to count pulses, this can do it. So these 1 second pulses are coming off that GPS synchronized oscillator, so very accurate time signal basically right here. It's like having a clock with 1 pulse per second signal. So the frequency counter again is functioning very, very well at this point, and it's ready to put back into service. The 5334B frequency counter project is now complete. If you enjoyed this video, don't forget to give a thumbs up. And if you haven't subscribed to this channel, now would be a good time to do so. I'll be covering many more projects like this in the future. So until next time, goodbye.